Hi,
Excellent.
everybody. Today we're going to talk about specifically sine amplitude estimation in environmental control modes. Here's the big question. Got this nice sine wave here. What's the amplitude of this sine wave? Is it 5 volts, 10 volts? Is it 3.5 volts? What would you pick, Charles?
I'm going to go all three, and depending on what someone's asking for.
You're too smart. Yes, it was a trick question because the answer is D, all the above. What amplitude number you assign to this sine wave very much depends on the scaling that you use. So this sine wave can be described as having a 5-volt peak amplitude, a 3.5-volt RMS amplitude, or a 10-volt peak-to-peak amplitude. You gotta make sure you understand these scaling values, and that's the beginnings of what we're going to talk about today. Because the big question here is, why doesn't this spectrum match the time domain data? We would expect somewhere at some point that with this time recording at 28 Gs, that we'd see something at 28 Gs in the spectrum here. But we don't, because what amplitude estimation method we're using has a big impact on control. We're going to talk about the amplitude estimation methods in a minute, but to start with, we have to understand why we're using them to begin with. Sine control doesn't use FFT processing. Sine sweeps move too fast for FFT processing to work. You'll end up with inconsistent spectral results. And here's an example. If you looked at these spectra, Charles, what do you think? Do you think they all came from the same test, or do those look like they're different tests?
That looks like it should be a different test.
Yeah, that would be my assumption as well, just looking at it, that these data sets all came from different tests. But really what this is the same swept sine time recording, just processed in 3 different ways with FFT processing. So different overlap values, different number of averages, all kinds of different settings can really affect what the result looks like. To avoid that, we're going to extract the control amplitude directly from the time domain data. But this can be a real challenge because if we're looking at what happens here in swept sine, we can see exactly what's going on, right? So this blue trace up top here, this is the drive voltage going into the shaker. This red trace is the time data that's actually measured on the control accelerometer. And there's noise on this and all kinds of junk. And what we want to see in an ideal world is this nice green trace that looks like a great sine wave. But again, we look at this green sine wave and we're like, okay, if this is the actual test and I'm actually seeing this in the time domain, but my controller thinks I'm seeing this, maybe I'm over testing. To address this kind of noisy sine issue and looking at this and going, okay, what's my amplitude here at any given point in time? We have 4 different answers that Test Lab can give. We have a harmonic estimator, an RMS estimator, an average estimator, and peak estimation. Now, if we have a real nice response, like this green sine wave, all 4 of these are going to give us the same answer. But if we have noisy sine waves or noisy responses, we're going to get different answers here. So let's take a look at these amplitude estimation methods, and then we're going to go into the software and run a couple tests and show you how they can affect the data. So the first amplitude estimation method is harmonic. You can think of this as a constantly moving bandpass filter that's being applied to the time data. So it suppresses all of the harmonics in the sine signal. We get this green junk in, and we get this nice sine wave on the other end going through the filter. We get really great harmonic rejection here. We also get magnitude and phase, but this is also our least conservative test. And I should define conservative. When we're talking about conservative in this sense, What I'm talking about is protecting the test article the most. Harmonic is going to give you your least conservative test, meaning that the drive voltages are going to be the highest for that. And we'll take a look at some data and we can see exactly what we mean by that. Now, the RMS estimator is the next amplitude estimation method we're going to talk about. And as you can imagine, the RMS estimator is looking at what's the area under the curve here. And you can see versus the harmonic estimator in the frequency domain, the RMS estimation is going to assign more value to this amplitude than the harmonic estimation. The next one is this average sign estimator. And again, versus harmonic, harmonic's going to give you a lower answer for what's the amplitude than average. And again, would lead to lower drive level than harmonic. And then our most conservative, meaning most protective of the test article, is this peak estimation method, which very, very simply just looks at the overall peak in a period, whether it's positive or negative. It's looking at the largest absolute value in a period. And again, you can see the peak estimator almost always across the board gives a higher value for amplitude than harmonic does. And so peak estimation is going to give us the lowest drive level. And therefore, I would call peak the most conservative test, meaning the amplitude estimation method that is going to give us the lowest drive voltage on the shaker and be most protective of our test article. There's drawbacks to these other estimation methods as well. As I mentioned, harmonic gives you phase information, peak does not, right? How are we going to extract phase information from simple peak value pulled from the time domain? Peak can give you issues with instability in your test as well. Let's take a look in the software and see what I'm talking about. So our first test we're going to run is using the harmonic estimator. I've got a pretty simple cantilever test article on my shaker here. The first channel is control. The second channel is an accelerometer on the tip of that cantilever. The third channel is the COLA signal. COLA stands for constant output level adapter. And that's going to give us a scaled voltage signal that corresponds to the frequency that the test's at. This allows us to do some post-processing or synchronization with a secondary data acquisition device. And then the fourth channel, I'm just recording the drive voltage so we can see what that looks like as well. We're going to use the harmonic estimator. It's a pretty simple quarter G sine sweep from 20 to 500 Hertz. Pretty simple, and I'm going to take the time data as well. So let's take a look here. I've already done a system identification earlier, so I'm just going to go in and go right into our test. I'm going to arm it, and we'll run a sweep here. And we can see what's happening. Right now I'm hitting some rattling. I have a bolt in a hole that's loosely tightened at the end of the tip of my cantilever there, so it rattles around a lot in certain frequencies. We're going to go through another area. We get a little bit of weirdness going on. And again, you can see what I'm talking about here. In the tip response, this harmonic estimator is always going to give us the lowest value, then average, then RMS, then peak. Peak is always the maximum value. Harmonic is always the least. Average and RMS swap sometimes. So you can see the RMS response is higher here than average. Got the same over here. Yep. Again, harmonic, then average, then RMS, then peak in increasing order of amplitude. Let's go back and we'll run another test and we'll switch our control estimator. Let's use RMS this time. I'll change the name here. RMS control. Go again. And we can see that this is giving us a lot more oscillation than what our harmonic estimator was doing. All right, that was our RMS used as control. Now we'll run a sweep with average. Do this real quick. Okay. Average control. All right, and we'll do our last estimation method. We'll do peak. And then we'll start to look at some of this data.
Sounds good.
Now we can see here this peak estimation method. This is this control instability that I mentioned before. Right, so harmonic really helps with that because it's rejecting basically anything that's not periodic in nature. So if you have any impacting or anything like that, which is exactly what I have going on here, peak has a hard time compensating for that kind of phenomenon.
I guess that's kind of the catch there. The peak being the most conservative for protecting your device under test, but it also could lead you to more aborts because it's not going to control as well. Kind of right there, what you just showed in that 30 to 40 hertz. Yeah.
Exactly. So let's take a look here and let's see. So first, let's just take a look at the time data here. So I'll use this from our most recent test, and I'll pull in my control channel and tip response. Maybe I'll move this up there. And then over here, we'll look at the harmonic control spectrum, and we'll look at the harmonic tip response. Now, a couple things to note here. First of all, this G level looks kind of nuts compared to what we have here. And one of the things to keep in mind, first of all, is if you're going to be recording sine data to get good fidelity in your result, it's a good idea to do 10 times oversampling. So part of the thing we're seeing here with this high G level is that we've got frequency content from higher frequencies in this time recording that's not going to be in our spectrum. The other thing is, if you zoom in here, you can see all the impacts. These are all transients from the test. And it keeps happening here as we go through that frequency. And then we get our nice sine wave again. So this starts to make more sense. We have our G level, and this is what we're seeing out here. We're around 2 Gs or so. So where is that? Probably somewhere in this area. And we can see that this goes down in amplitude, down in amplitude. The scaling is changing. So if you look at this number here, as we scroll through, we're seeing that G level goes down and down and down and down. So now we're at 0.76 Gs. So we're somewhere in here in our sweep. Let's keep going here. Continue to go down. right. Zoom out a little bit here. And we'll see where we're going to go into this region. So you see here, we're in this area here where the tip response and the control channel are about the same amplitude. And now we're going to go, oh, there we go. Now we've suddenly jumped back into this region, right? So we're at about 0.9 Gs there. Yeah, somewhere in here, and then we jump up. You can see, looking at that, what's going on in the time domain is at some portion here, we've got a nice sine wave. And then for most of it, we don't. So let's do this. Go back into harmonic control. And I'm going to put this in the input basket. And I'm going to turn on my time signal calculator. And we'll pull this in from the input basket. And you can see my two traces here. So the first thing I'm going to do is just put in a low pass filter here. We'll make it real easy. All right, channel 4. And we'll do the low pass at 500 Hertz. And we'll just keep this the infinite impulse response type. So let's calculate here and take a look. Okay, and you can immediately see the difference. This red trace having this high frequency noise in it, and then we have this calculated trace that's giving us more of an answer that we might expect. We've now gone from this, why am I getting 100 Gs in the time domain, but my spectrum is only showing a max of like 3 Gs. So let's see where we're at here. If I put a cursor on here. Okay. Now we've got a much lower G level than we had before because we're only looking at 500 Hertz data. This can be real confusing to think about too, because G levels aren't always the best indicator of what's really happening in a test. Even though this seems like a really high G level, it's a very short duration impact kind of thing, and the frequency is higher than 500 Hertz. So my displacement is really small. There's a inverse square relationship between displacement and frequency. So the higher in frequency you go, the lower in displacement you're going to get for the same G level. So there's kind of a question there of, okay, am I really worried about it? And that's where the harmonic filter comes into play. If I'm exciting higher frequencies and getting higher harmonics, then maybe I'm not really so worried about using that. But if you think in terms of electronic components that you might be trying to monitor and protect, using a peak value might make more sense because we're talking about high frequency stuff that might affect your electronics. If we're talking about a hunk of steel, we're more worried about our low frequency responses. So that's kind of the first thing to think about here. I think the next thing to look at is between the different runs that we did, we can actually look at the time data of the drive there. So we'll put harmonic in, then we'll put our peak in, then RMS, and then, there's average. And I'll go into options and I want to display the run name here. There we go. Okay, harmonic, peak, average, and RMS. And we can see right away, just look at this first section. Again, harmonic is giving us, I'll zoom in even a little more here. Okay. So harmonic is giving us our highest drive voltage. That means it's putting the most force into our test article, followed by average, then looks like RMS, and finally peak, giving us our lowest drive voltage. Lower drive voltage means that we're putting less force into our test article. In terms of protection of our test article, peak is the most conservative, harmonic is the least conservative. Now, if we're talking in terms of over test or under test, peak would give us our most potential for under test, and harmonic gives us our least potential for under test. The other way to say that is harmonic gives you the most potential for over test, and peak gives you the least potential for over test. You can see the same thing if you look at the spectrum of the drive channel as well. We'll go into, spectrum. This is for harmonic control. We'll go into average, and then RMS, and then peak. And you can see very drastically the differences in what's going on here. When we went for that first resonance, average, RMS, and peak were going down in voltage, where the harmonic actually increased in voltage there, right? So that's kind of an interesting observation. There's another area out here where peak actually went higher than the other two.
Thanks for joining us today. Have a great day. Thanks, Chris.
Have a good one. Thanks, everyone.